and he's a lecturer here in the stats department and one of the core members in SEEC. He uses machine learning to solve environmental issues with spatial analyses and also remote sensing data. And today we'll be speaking about spatial interpolation. So thanks, Azza.
So afternoon. As Bianca has said, I'll be speaking on spatial interpolation. So when I had to talk about this topic, I was stuck for a bit. I thought maybe I should bring all the methods and discuss all of them, but some of these methods are of little to no use. So what I've just done is collected a few of the methods, which I think is the best practices. So spatial interpolation is basically the idea of you go out to an area, you sample at a few locations, and you want to make a prediction at a new unsampled location. All the methods basically use the idea of you expect things closer to each other to be more similar than things further apart. So if I've got a sample at one location quite close to my unknown location, I would expect the two areas to have a similar value. So as I said, I'm not going to discuss all interpolation methods. I'll just discuss three, which are inverse distance weighting, splints, and kriging. But before we go into the specific methods, we'll look at the spatial interpolation problem in general, then look at interpolation as a deterministic method and as a stochastic method. So we'll make the two categorizations of our interpolation methods. Okay. So, spatial interpolation is a very common. You might want to go out into an area, you've got a study area, say you want to know soil pH. Obviously, you cannot sample the whole area to determine soil pH over the entire area. What you usually do is pick or have samples at few specified areas. From then on, you can make predictions about the soil pH at any of the other locations. Obviously, what usually happens, you don't just want to make a prediction at one location, but you want to create a surface of whatever you're studying. So, say in our soil pH example, we don't want to just know the pH at that point, but would like to create a surface of soil pH over that domain. So that's the very general problem. So what we usually do is weight our observations such that they give us an estimate of the unknown value. Because we're saying that we expect objects close to your sample location to have information on that sample location. So the general form of our estimator then simply becomes a weighted average of the values at the sampled locations. So that's your weight and those are your sampled values. And you just weight them depending on some lambda I. So lambda I is just basically how much you expect point I to influence what you are seeing at your unobserved location at O. So you have to determine those weights. You also have to determine the number of points which you think affects that particular point. Although we know that this is a whole domain, we are saying that only a few of the points will affect a particular point. We do not expect very distant points to affect your unsampled location. So you have to determine what you think would be the number of points that affect your unsampled points. So the two very broad classes of interpolation methods that can do this, they are called stochastic and deterministic interpolation. So the first of our methods, deterministic methods, are basically mathematical functions. You create a mathematical function and you fit it over your surface. Examples of such interpolators are your global and local polynomials, which are basically regressions on your coordinates. This is a very poor interpolation method because it does not really use the information in your data and assumes that the relationships in your data are strictly determined by your coordinates. There are more sophisticated methods. There is inverse distance weighting, and there's also splines. So I'm sure is quite familiar with this. In all these deterministic methods, we do not make any assumptions about our stochastic process, and we just assume that closer points are more related than more distant points. And when we're fitting these models here, we have to pick the parameters. There's no way of objectively estimating the parameters of those three models or any other deterministic models. So you have your deterministic model, you fit. Then you can also then judge the accuracy, overall accuracy of your fitted model. And this is done via cross-validation. Cross-validation is simply you've got your n sample points. What you do is fit your model with your n-1 point and predict at that nth point. So you do that for all of your points. This should give you a measure of the overall accuracy of your model. So you're basically your average prediction error. So cross-validation is widely used for most learning methods and quite widely used in machine learning. And basically, these methods are basically just learners of the same form you see in machine learning, where you take your data and try to find some structure in it. We also then have our stochastic methods. These methods use both mathematical and statistical techniques to predict values at our unsampled or unknown locations. There are generally 4 classes, although I've only just given 3 here. There are 4 classes. There's your machine learning based methods, such as your support vector machines, random forests, and neural nets. There are your Bayesian methods, such as your maximum entropy. Then there's your classical stats methods, which is basically regression on the coordinates. Then there's also geostatistical methods, namely cribbing. So under our stochastic methods, we specify or we state out some very strict assumptions on our process. So if we've got rainfall or whatever we put some assumptions on that process. That then allows us to estimate the parameters of our models in a objective manner using probability theory. Where before in the deterministic case, you just say, okay, I think that this parameter is X, then you run that model, check your cross-validation and see how it looks. Here we're more objective as we're using probability theory. So with the stochastic methods, as before with the deterministic methods, you can check how good your average predictions are using cross-validation and your root mean squared prediction error. But in addition, you can also judge the accuracy at a particular point. So remember our root mean square prediction error there, which you obtain by cross-validation, is telling us about the overall performance of our model. With the stochastic methods, we can say something about the overall performance of our model, and we can say how well our model is predicting at a particular point, which can be very important. Let's say we're working with pollutants. So you might want to be very specific on how well you estimate your pollutants. If I'm estimating my pollutants at a point close to a mine, I don't really maybe care about how good my estimate is. But if it's next to a children's hospital, I might be a bit more stricter in my prediction because I want to have a better understanding of the variance or how much my pollutants vary. So you cannot do this with our deterministic methods, and you can only do this with our stochastic methods. This then sets apart your deterministic versus your stochastic methods from each other. What we've done now is just basically categorized our interpolators in terms of stochastic and deterministic, but there are many other ways of categorizing interpolators. There's the exact versus approximate categorization. convex versus non-convex, and local versus global. With the exact versus approximate interpolators, we are basically saying an exact interpolator will predict the value you have observed. If I have a sample and if I have a location and I have sampled that location, when I make a prediction, I should get, my prediction should match exactly, my prediction there should match exactly what I have observed at that location. Those are the exact methods. With the approximate methods, your prediction may not match your observed value. Then with the non-convex convex categories, we're saying the interpolators for the convex or convex type of interpolators are restricted such that all your predictions are between your maximum and minimum observed values from your sample. With the non-convex interpolators, your predictions may be lower than what you've observed as your minimum in your sample, or they might be much higher than what you observed as your maximum for your sample. I'm sure already you can appreciate that some things you might want them to have exact interpolations, and some things may have approximate, and some things you might want to constrain them such that they are within your sampled values, and others you might let them go outside of your sample values. Then the last category, not so important, is the distinction between local and global interpolation. Global interpolation, basically, for any one point, when we're making a prediction, we use all available samples to make a prediction at a location. For the local case, we're a bit more stringent. We just want those few points which are quite close to that location. So we made a distinction. So we have looked at our interpolation methods and made a distinction between deterministic and stochastic, and said it seems like the stochastic method has more applicability as it gives a prediction F. But it might be worth going through some of the deterministic methods. So I'll quickly discuss inverse distance weighting and then quickly discuss ins. We have said that IDW is a deterministic interpolation method, and besides being deterministic, it is an exact and convex interpolation method. The method is global, that it uses all samples to make a prediction, but when it comes down to practice, if you've got a very large data set, say of 1,000 points, you do not want to use all 1,000 points to make a predictions when creating a map. So what usually happens is you have to define a neighborhood. This can be done automatically within the different software, GIS or R or GRASS, or you can specify some neighborhood yourself. Then we said, remember that our predictions are a weighted average of your observed values. And we said those weights, we want them such that points close to your location are given more weight, and points further away from your location are given less weight. In IDW, the weights are simply inverse functions of the distance between your samples and the unknown location. Then this parameter p is any integer. When you are using the method, you have to determine the value of p. As we've noted already that there's no objective way of determining p, and from your experience, you might then say, I think p is equals to 2 is good, p is equals to 3 is good, and so on and so forth. What commonly happens is that they use p equals to 2, which is the inverse squared distance. Another thing we can note about IDW is that our predictions are very sensitive to sample points. Where you've got areas of dense sampling, your predictions would be quite good, and where you've got very sparse sampling, your predictions may be very poor. But this is not unique to IDW, but it's the one which is most severely affected by your sample locations. And we can just quickly note that it works very well where you're interpolating surfaces or interpolating phenomenon that can change quickly over short spatial scales. Say maybe elevation. Elevation can sometimes change quite quickly. There it might be flat, then have a ravine or have a mountain. So it works for such a kind of phenomenon. Things like rainfall, not so much. Soil type and soil characteristics change at a more gradual scale. So I will not use that for them. We've got a slightly more sophisticated than the IDW. Remember, in our IDW, we're taking our weights simply as an inverse function of the distance between your samples and your unsampled location. Here, we've got a little bit more complex estimator. So that's our estimator over there. But before we get to that, let's note the basics about splines. So splines are just polynomial functions, which are local, non-convex, and exact interpolators. You know what's the meaning of that? So there are basically two types of splines that are used for interpolation. There's your thin plate splines, and there's your regularized spline with tension. Your thin plate spline has got one parameter, and your regularized spline with tension has got more parameters, giving you more control over the surface you build. And we always want to try to have more control over what we're doing. So I think the regularized spline is a better interpolator of the two spline methods. Okay, so let's see how we get a prediction at a location. We have some constant, and we then have some weights. So these are the weights in the method, and some function RPF. So this is basically a radial basis function or a kernel. When you are trying to fit a spline model, you basically have to solve this system of equations to get your parameters. But obviously, to initiate that, you have to have some values for your weights and for your smoothing parameter. And these have to be determined by the user. Every time a user has to determine stuff from their head, I always think that's a bad method. You should always let the data speak for itself. Okay, then we just said that with the regularized spline, you've got more control, and our smoothing parameter here basically controls how much below or above above your predictions are to the surface points. Basically, here was just saying that parameter controls how much above the range or below the range you get. So remember, we said our points was this sample points with the maximum value and the maximum value. This parameter controls how much you want to go above that and how much you want to go below those values. As I said, these parameters have to be determined by the user. What usually happens, you pick a few parameters, you cross-validate and see which of those parameters will give you the smallest root mean square prediction error. Quick recommendations is that if you're using the regularized spline, you should choose weights between 0 and 5 for a tension spline. Also 0 and 5, we just say weight values must be greater than or equal to 0. You do not want your weights to be equal to 0. See, there's lots of subjectivity coming into here. It works best for interpolating gently varying surfaces. We noted for IDW that it works well for interpolating surfaces which can change rapidly. And here we're saying it works best for surfaces which change or phenomena which change more gently with spatial scale. So those were our two deterministic methods. They are very good methods and they work well for most problems. If you just want to if you just want to, excuse me a second. It will last. Yeah. So if you just want to create a surface and do not want to use that surface for any decision making, then ITW might be fine. You just want to create a map, or your thin states, your spins might be fine because you just want to create a surface. You don't care how much or how good your predictions are at that particular point. Then just stick with your deterministic methods. But if you want to say, if you want to create a surface, then say how well you are making predictions at the different locations over your domain, then it's best that you use a stochastic interpolator such as kriging. The other methods such as of machine learning, such as support vector machines, that are fairly recent, and I think I saw they've been widely used mostly from 2014 onwards. Before then, it was strictly geostatistical methods of kriging. Even then, when I look at the methods, I still think they fall quite short to kriging, although because even if they give you a prediction and a prediction area, they do not describe the process as well as a kriging model does. So we'll see how a kriging model describes or characterizes a process. So what do we note about kriging? It's a non-convex interpolator that can be inexact or exact. So it's already quite flexible. The kriging interpolator is based on the concept of spatial random variables being partly deterministic. So we've got some mean part which is deterministic and being partly stochastic. So that is some random component. So that would be your, so then that random component has a mean of 0 and has got a variance covariance matrix parameterized by theta. We'll get to what those parameters are later on. Let's note one more thing about the model. Our deterministic trend, is commonly modeled as a function of the observation locations by polynomial functions. So you can take your coordinates and basically create polynomials from that. Simple polynomials of the coordinates, which are mathematical functions. Agreed? So that would be the deterministic or mathematical function part. Then here you have to have some statistical assumptions to that. So we have said that under the kriging model, our delta there is a zero mean process with a variance covariance matrix with some parameters theta. So the Q of these parameters. We also note that our stochastic component can be further decomposed into two parts. So we're saying this is the random part of our process, and we can decompose that random part of our process further into two components. The first component here is telling you about the structured variation of your process over the domain, and your epsilon there is basically random noise. Okay, so it's just a random process with no structure to it. So what are those Q parameters which are parameterizing our covariance parameters? We're saying these parameters correspond to some aspect of our process, and if we're estimating, or when we estimate them, we can have or we can gain some insight into our process. Usually there are 4 of these parameters. There can be more, but most of the functions we work with have only 4 parameters. The first parameter, which is called tau squared, is basically the variance of our random noise process. So it's the variance of that unstructured stochastic process epsilon. Sigma is the variance of the structured part of our process. So that's the variance of eta. Obviously, so we're saying tau is the variance of that part, sigma squared is the variance of that part. If you add the two variances, they'll give you the variance of our process. Okay. We also note that there's another parameter phi over there, which is basically telling you what is the maximum distance over which you expect points to affect each other or to covary. Remember, our very first assumption is that points closer to each other affect each other more than points further away from each other. So our phi is basically telling us at what distance then does it not matter. So the 2 points are basically, not I won't say independent, but it's a good word. So the 2 points are basically independent of each other. So they do not affect each other so much. So that's our phi parameter. Then you've got also a smoothness parameter, basically telling you how the process changes over the small spatial scale. As you can see now, if we estimate these parameters, we gain quite a lot of insight into our process beyond just predicting at a point. So we said these parameters correspond to what is termed the semi-variogram of the process. Semi-variogram of the process is basically a function related to the correlation of a process. I drop. And we know the correlation function should decrease with increasing distance for any 2 points. The semi-variogram is basically 1 minus that is equal to 1 minus your covariance function, such that it has the shape something like that. So it's just the opposite shape of your covariance function. So in geostats, we prefer to work with the semi-variogram instead of the covariance function. So those parameters correspond to our semi-variogram function, and obviously by extension to our covariance function, because we just have that simple, straightforward relationship. So these parameters, or our semi-variograms, can be modeled, and we've got parametric models for this. So here are some of the most common parametric models of the semi-variogram. Remember that these functions are functions of the distance between any 2 points, because remember, we want them to characterize how any 2 points vary given their distance. So the functions of h, and you can see as we take the first line, our exponential variogram, here we've got our nugget variance, there's our tau, there's our sigma squared, and there's our range parameter over there. So the smoothness parameter kappa is not in all functions. It's only there for the Martin and the Cauchy distribution. But most just have tau, sigma, and your phi. So all of these functions have the general shape given over there. So this is the general shape of our semi-variogram models. The dashed lines being an exponential semi-variogram, thin line being a spherical, and big black line then being a Gaussian semi-variogram model. Here I've given them the same parameters. So they've got a nugget variance of 0, a partial seal of 1, and a range of 5. So this is the range over here of our 5. So points beyond 5 here should not affect each other. We only expect points at 5 or below to affect each other. Okay, then we can note one last thing about kriging. Remember, in all of this, we want to obtain weights that will weigh, basically, weights that will weigh our observations. So saying basically for the particular observation, how much do we think it affects our prediction at the unknown location. So to determine this weight, we basically just minimize that prediction error given over there. So that minimizing of that prediction error can be done in several ways. We note that the main assumption of kriging, remember we said in deterministic methods, we are making no assumptions about the process. And we said for stochastic methods, we have to make some assumptions about the process. Remember, in statistics, to make any headway, you have to make some assumptions. And these are, in essence, statistical methods. So in kriging, we make the assumption of stationarity of the process, and various levels of stationarity can be assumed. We can assume that the process is strictly stationary, so the mean and variance are constant throughout the observed domain. We can make an assumption of second order stationarity, where we say the mean is the same everywhere and the covariance exists. That depends on the distance between points. And intrinsic stationarity is basically a non-stationary process. The mean will change with location, but our covariance function still exists. We need the covariance function to exist at all points, so we can calculate our semi-diagram. If we don't have covariance function, then we cannot calculate anything. So the most important thing here, or the most important implication of the stationary assumption, it allows us to define the covariance and hence the semi-variance. Then we say the stationary assumption affects the form of the mean. Obviously, if we're saying that the mean is the same everywhere, it should be different from where we're saying the mean changes with location. So how would then the mean of our process, remember we have a mean for the process, which you said is deterministic. So how would this mean then look? And I teach too much, I feel so used to chalk. We said our z is given by mu plus delta, and we know that our mu over there, and that's our mean of f theta. So we're saying the mean can change over our locations, over our domain, which gives us the non-stationary mean. Okay? And the mean is unknown. So our mean varies over our observation domain, and we do not know the mean. So we model the mean as f beta. So this is a matrix, and that's usually a matrix of our coordinates. We can assume that our mean is constant but unknown. So now we do not need the coordinates. Remember here we're saying the mean is constant over the whole domain. So we just have to estimate the mean. It does not change over the domain. And then there's also a situation where we're saying the mean is known and constant. So you can see with kriging, we're pretty flexible. We can model constant means and we can model non-constant means. Okay, that's all the theory. So let's go into how do you fit, or how would you then fit a kriging model. There are essentially two ways of fitting kriging models. There's the least squares approach, then there's maximum likelihood approaches. So in fitting the models, basically we want to estimate those Q parameters. In our first approach, we try to estimate what we call the empirical semi-variogram. So we try to estimate the shape of that curve from the data. Then once we've obtained the shape of that curve from the data, we then try to fit one of the theoretical models by minimizing the deviation between your fitted curve and whatever you've estimated. So you're trying to estimate this curve. You might have some points over there. Then you try to minimize your sum of squares between your fitted and your observed points. So let's see how that would look in practice. You've got however many data points you have. The first step is to compute the semi-variance between any 2 points. So you basically have to know for any 2 points what is the semi-variance? Obviously, the points will have different distances to each other. Take just here, so I have to calculate the distance of just to Vern, to Bianca, to Greg. So for each point, I have to calculate how far it is from each other, from each of the other points, and then have an estimate of the semi-variance. So this is our first graph here. So we've got the distances of the points to each other, and this is the semi-variance we obtain from those points, which is very messy. So once you do that, then you have to basically smooth that graph out by taking a histogram approach. So you then say, okay, for at distance 1000, let me group all these points at 1000, and what is the average semi-variance for all those points at 1000? For 2000, again, group all the points at 2000, what is the average semi-variance at 2000? Then in the end, you end up with that smooth curve over there, obtained by this here. So here it's just telling you how many points did you use for each of those estimates. And you can see at the shorter scale here with 234, here at 4000, we have roughly 1840. So you will not use the same amount of points to estimate the semi-variance, which with the corner pro would say. So once you've done that, you've got all those theoretical models, and then try to see which is the best fitting of your theoretical models. From then, you should be able to obtain your parameters. Okay, so that's the least squared approach. I am not a big fan of this Bird's approach because it's very subjective. You have to basically determine. Remember, you've got that this messy picture here, and you have to smooth. So you have to make subjective decisions about how many points do I use to calculate each of these points, and you also have to make a subjective decision of where do I even place those points. You could use 5 points, or you could use 6 or more. So it's very subjective. How many points do I use, and where do I put those legs? So I'm saying there's no formal way of determining the number of places where you have to calculate that semi-variances, and there's no formal way of determining the number of points you should use to calculate each of those estimates. So it's very subjective. There's always a way out. So what's the way out, or which is a more objective way of doing this? We can use a likelihood-based methods. In the maximum likelihood setting, that's our log likelihood to maximize, and in the restricted maximum likelihood setting, that's our log likelihood to maximize. So there, we are not doing anything fine, we're letting the data speak for itself. Unlike in the previous setting where we had to calculate semi-variances, group them into that histogram, then do some fitting on it. So there's a lot of steps in between which are not result objective. Here with maximum likelihood, we know our likelihood functions. We can just optimize and then obtain estimates for our parameters and for our beta over there. Very objective. Then another pro about likelihood methods, besides the objectivity, we can always get our goodness of fit stats, your IPI, your AIC, and your Bayesian information criteria. From there, we know that our AIC and BIC allows us to compare different models, which is a big pro of AIC and BIC. So now we don't have to rely strictly on cross-validation to say which is the better fitting model. We take data, fit a model to it, get our parameters, and check using the AIC or BIC to see how good a fit that is. Okay, then we can come to the last point. So we said, okay, the whole point about stochastic method is that they allow us to have a prediction for each of our points, not just to have or to have a measure of the accuracy of the predictions at each point, and not just tell us we think our model is doing well on average. So we can say at each particular point how well our interpolator is doing. So with that, we can create a prediction surface. So besides creating our surface of interpolated, say, rainfall values, we can then say how we think those values variate using prediction errors, and by extension, we can calculate confidence intervals for our predictions. It is a big problem. Okay, this is the very last slide. So we know we can calculate the prediction error at each of the points. So then how should you, or how would you calculate this prediction error? So this is a bit theoretical. I won't go into details, but I'll just tell you what are the different estimators of our prediction error. So that prediction error at a particular point for kriging is called the kriging variance. And there exists numerous estimators to estimate that kriging variance. So the first three here are analytic estimators, so we have closed form expressions for them. And these two here are simulation-based estimators. So Monte Carlo type estimators, and here the analytic estimators. The very first estimator here is our traditional estimator. What happens, or how you get estimated for our predictor, we have a closed form expression that tells us how good the prediction error is. What happens with the closed form expression is that you take your estimated covariance parameters, substitute them into the expression, then calculate your kriging variance. This happens for most many situations where we have a closed form expression. Take the estimated parameters and use the estimated parameters as if they were the true parameters. Obviously, by doing that, we are introducing an added source of bias, because you estimated the parameters that are not your true parameters. So this leads to our traditional plugin estimator underestimating the true prediction error. So the other estimators 2 to 5 were designed to correct the bias of our plugin estimator. So the Kaka-Hebel and Prasad-Rao estimator use the traditional estimator and then add a correction term to them. Then, as we said, these two are Monte Carlo based. So my last words of wisdom are that you should please avoid using the plugin estimator for kriging, and it's better if you use the Prasad-Rao estimate. It gives you less bias variance estimates. Also, I would say it is best that you use your Prasad-Rao estimator with realm and estimation. If you use realm, no matter what estimator you are using, it will be less biased than if you're using maximum likelihood. But I'm just saying for the very best estimator, use realm in conjunction with the Prasad-Rao to get your best estimator. Okay. So this is a very wide topic, spatial interpolation, and these are the 4 references I'd like to point you out to. Deagle and Roberio is a modern text where they're using the likelihood methods which I showed you earlier on. Horvath uses the more traditional methods for interpolation, and is in for kriging. They use the more traditional method of estimating parameters, which is the least squares approach. Then here, Lee and Heap give you a nice overview of the different interpolation methods that are used. So to give you the categories of stochastic and deterministic, exact and exact, and also discuss the different estimators. It's a nice review paper. And this last paper here just goes into the details of where do you get the source of bias in the kriging variance estimator and other discussions. So these are the people who suggest using the Prasad-Rao estimator with Okay, so that's my take home then. Use kriging for interpolation. Stay away from the others. Treat models using likelihood methods. The rank is to be preferred. Then estimate your kriging